which side of a shape the area vector is going.
So if there is no current in the loop, then it has to be perpendicular to the plane of the loop, and it's arbitrary, it's either one.
Okay.
But if there is a current, like when you calculate the torque on it or the net force on it, if there is a current in the loop, the area vector will, you have to select one of the two possible directions that are perpendicular to the plane of the loop. So you can use your right hand and curl your four fingers in the direction of the current around the loop, and then your thumb will tell you the direction of the area vector that you select out of the two possibilities.
Is it something you can guess, and if it comes out negative, you know your guess is wrong, or is it
But what do you
something,
mean negative?
to answer? I'm probably wrong on the type of question that's being discussed, but I remember a lot of times, like, when you have to pick a direction in the formula, and you get it wrong, the answers typically like the result is.
So, I mean, if it's asking you specifically for the torque,
Oh, okay, then that one, yeah.
then then it would be the torque is the magnetic dipole moment you cross into the magnetic field.
Oh,
And the magnetic dipole moment for the loop, is calculated by using the direction of the current in the loop. So there's no way to get out of it.
okay, I see.
There is a specific answer. Now, for the questions from chapter 29 having to do with the induced voltage, right? Then normally I ask for just the magnitude of that induced voltage, right? Because there is a minus sign in the expression in Faraday's law, but that minus sign is really there to tell you something about the direction of the current that will result of the induced current. And to get the direction of that induced current, I use Lenz's law.
Okay.
So there is kind of arbitrary, but for calculating like the torque on a loop, then there's no choice. I mean, it is not arbitrary. There's a specific answer. Yeah. Any other questions?
What's the first next Wednesday on?
Most likely chapter 29. Yeah. 27. This week, which I finished last week, I think, because I'm almost done with 29. I mean, we talked about Lenz's law, Faraday's law. So I'll just finish chapter 29 pretty much today and then move on to chapter 30. And I'll spend, a good part of this Wednesday in chapter 30, next Monday in chapter 30, and then we'll have some time, and I'd like to make some remarks about chapter 32. So we won't have time to cover chapter 31, so I'll skip chapter 31, and then I'll say, as much as I can in chapter 32.
What about chapter 31?
Hmm?
What about chapter 31?
I'll skip chapter 31.
Okay.
It's a very long chapter. Yeah, and there are a lot of details in it. It's an interesting chapter, but they're just you end up with differential equations, and then you have to remember a lot of tricks. So I think you'll get more if I discuss chapter 32 and not do 31. 31 when you know more math, then you can tackle that one. Any specific problems from chapter 30 or 27? No? Okay, so if you don't have questions, then, and then we're gonna do one more lab, that's this week, and that lab is going to be on transformers, which is, actually I have an extra example from chapter 29 on it, so I'll go over that today, and then you'll do that lab this week on transformers. Sounds like a plan?
I believe there's only 3 weeks left.
Yeah, I'm beginning to see the light at the end of the tunnel. Last week I couldn't see it, it was like, but now I'm beginning to see it within reach. Okay, so this is the these are the weeks when, you just tell your friends, I'll see you in about 3 weeks. Because I'll be very busy. This is when you need to catch up, review, and then, you finish school, and then you have more time to do other things. So. Whatever that was. Okay. So, all right. So, there we go. Maybe I'll begin with, instead of continuing with the lecture, let me do, I think there is one example from this chapter that I haven't done, and it's the one that is related to transformers. Because I think we did examples 1 and 2, and I like to talk about number 3. The result of example number 3 is actually quite simple. Okay, let me tell you the result, and then I'll show you how you can obtain this result. But it is a result that it's simple to work with. So the idea is the following, and the way we're going to do it in the lab is like this. So the way we're going to do it in the lab is as follows. So there is a coil with many turns. So let's call this coil number 1 with N1 turns. So it's a very long wire, and imagine you grab a wire, right, and you go like a very long wire, and you go like 1, 2, 3, 4, 5, 6, N1 turns, okay, of wire. So it's a coil with N1 turns, capital N1 turns. One end of this goes like this, the other one goes like that. I mean, it's just one very long wire, right? And then over here, you have a power supply, which I'm going to write as plus minus, something like this. Okay? And suppose the current, well, in this, I mean, you can think of this as a, if you like a plus minus like this. Maybe this will make more sense to you. The current in this segment of the wire will be which way? Given this connection, the way the circuit looks. It will be to the
clockwise.
So at this point, it's going to be
To the right.
to the right. So the current is going to be to the right. So the current is going to be this way, right? And then the current is going to go to like this. And as the current goes like this, and then back like that, what will be the direction of the magnetic field generated by this current in this coil? So it goes like this, right? So this is going to be like a solenoid. So the magnetic field generated by this coil is going to be, at that instant, is going to be up. Yes? Up the coil. All right. And then we have another coil over here. Let's call this coil number 2. Okay. We can consider this like a discussion of this week's lab, if you like. And then you just minor details in the lab for some of you tonight, for the rest of you this Wednesday night. This will have N2 turns. All right, and this other one here has a how can I say this? These terminals are connected to a, shall we say, like a voltmeter? Okay. So we have a voltmeter. You know, those multimeters that you can use to measure resistance and current and so on. And then you have 1, 2. This one is COM, that's the black one. And then there's a red one over here, another port over here that either says voltage or ohms, right? That we use to measure the resistance of a resistor that was given to you. So let's say you take this and you connect one of these to that and the other one to this. Notice, this is a voltmeter designed to measure the voltage induced in this coil. This is not a power supply. This is just a measuring device of the voltage, you know, across this coil here. This is a power supply. This is something that generates the current. Okay? Now, what we want to do is we want to send this magnetic field. And remember that the magnetic field forms closed loops, right? So the magnetic field goes out over here, right? So what we want to do is send this magnetic field over here. So it goes there. It will be going like this, right? And it's going to come out and it's going to go there. Right? Okay? Now, if this is a DC voltage source, if this is a DC voltage source, this current might be 2 amps, 2 amps, 2 amps, 2 amps, 2 amps. This magnetic field will be so many Tesla, so many Tesla, so many Tesla, but it will be the same magnetic field. And therefore, the magnetic flux through this coil is going to be whatever, the same, the same, the same, the same. And this guy is going to read 0 here. And by the way, remember that this voltmeter has like, or multimeter has like something like this. This is the off position, and then you have various segments over here, like for ohms is over here, and for amps is somewhere over here, for AC voltage is like over here, for DC voltage is like over here. So and there's a reading, right? A screen over here, right? A digital display where you read off the voltage, right? Between those two, you know, ends of these wires. So if this is a DC voltage source, like, you know, a set voltage here, the voltage, of course, this is called E1. Then this will be constant, and if this current is constant, this magnetic field will be constant, and if that magnetic field is constant, since the area of this loop is constant, then the magnetic flux through this loop is going to be constant, and the voltage over here is going to be 0, which is boring. Right? So instead, what's done is the following. Are you following what I'm saying here? Remember that the voltage is induced by Faraday's law. The voltage is induced by a time-changing magnetic flux. The magnetic flux in Webers is the magnetic field divided with the area vector, which will be the magnitude of the magnetic field times the magnitude of the area vector times the cosine of the angle between the magnetic field vector and the area vector through some loop, or, you know, right? So, and there will be an induced voltage, which is, an induced EMF, which is written as minus the derivative of the magnetic flux with respect to time, right? So, if the magnetic flux is, through some loop, is changing with time, there will be an induced voltage, and that's going to lead to an induced current, right? Which we found the other day, like this, right? Just using Ohm's law, right? But if, given this setup over here, I do have a coil here, I do have a coil over there. If this voltage source is DC, direct current, right? Then the current is always going to be in the same direction and of the same amount. And so the magnetic field that it produces in this coil is going to be whatever it is, but it'll stay constant at whatever that amount is. Some of the magnetic field lines are going to go through this loop, and that'll be constant if nothing is moved, and if this voltage is not changed. And if there is a constant magnetic flux over here, if the magnetic flux is constant, its derivative with respect to time is 0, there's no induced voltage over there. And you just read that. So what we are going to do in the lab is we're going to replace this voltage source, over here, by a sinusoidal voltage source like this. So now this is going to be pretty much the following. We're going to have we're going to have a source of voltage, and if we have time over here, like let's say in seconds or whatever, the voltage is going to be something like this. It'll be time dependent. For the DC battery, that I was considering a while back, let's say this was delta V in volts, and this is time. Right? What we had was something that was putting out a fixed voltage, like that. This is a DC voltage. It was always the same. Actually, you measured using the oscilloscope at the beginning of the semester the voltage across the terminals of a DC battery. You picked a DC battery from a box that had various DC batteries, and the voltage was always the same, right? So if this is one of those DC batteries, and you represent this by a symbol like this, plus minus, right? That's what we've been using throughout the course. Then the voltage is always the same. If the voltage is always the same, then the current is going to be the same. If the current is the same, the magnetic field is going to be whatever it is. It's going to be a magnetic field, but it will be the same, constant is what I mean. And the magnetic flux is going to be constant, but the induced voltage is going to be 0 in this coil because the magnetic flux through it is constant, right? That magnetic flux that induced voltage only exists for as long as the magnetic flux is changing. So if I replace the DC battery by a voltage source, like using the function generator, for example, which I can select, with the function generator, there are 3 possibilities for the waveform of the voltage. I can choose it to be triangular or square, and we use this for the RC circuit, or sinusoidal, like a sine wave, right? So what happens in this case is that, for example, this is 0, right? This would be the voltage amplitude, like delta V, maximum. That's the amplitude. So during this time interval over here, the voltage is changing, and it is positive, right? So if the voltage is changing and it is positive, let's say for that interval, if this is plus and this is minus, then the current is this way in this circuit. The magnetic field is this way, and some of this magnetic field is going to be going through this. But because the voltage is changing with time, because the voltage is getting bigger, biggest, and then smaller, but still positive, if this voltage is changing with time, then this current is going to be changing with time. And if that current is changing with time, if I think of this as a solenoid, for example, this would be like mu naught Ni, right? If this current is changing with time, then this magnetic field is going to be changing with time. And if this magnetic field is changing with time, the magnetic flux through this coil is going to be changing with time. And if there is a magnetic flux that's changing with time in the other coil, there will be an induced voltage over here. And now the voltmeter is not going to read 0, it's going to read something. It's going to read this. Whatever that is, it won't be 0. It'll read something. Got it? Or no? No? And you probably are still in chapter 27. Yes?
If you were to move the coils, like further and closer away from one another, it would also cause it to change though, right? 'Cause you'd be
Then the magnetic flux would change. It would get bigger, smaller, depending on whether you moved it closer or further away.
Okay.
But in a transformer, you don't want something to be moving like that. So instead, you change the source of the voltage. You make it so that the voltage is changing with time. And during this time interval over here, the voltage is changing from 0 to a maximum and then back to 0. But still positive, so that the polarity is maintained during that interval. So the current is like that, the magnetic field is like this. But this magnetic field is going to be changing in response to the current changing because the voltage is changing. And if that magnetic field changes, then you're going to have a changing magnetic field over here, which will induce a voltage in this coil. And that is what you would measure with the, voltmeter over there. Now, what happens during this other part of the cycle? During this part of the cycle, the voltage is not just changing, but it is also negative. Essentially, what happens there is that during that part of the cycle, this polarity over here is flipped. Now this becomes negative and this becomes positive. So now this is negative and this is positive, and therefore the current is not going to be that way anymore, but the current is going to be this way. Right? And the current is going to be that way. And when that happens, right, now since the current in this primary circuit is the primary coil, this is the secondary coil. Now, with the current switched in direction, this magnetic field is going to switch in direction. And instead of coming out this way and then going in like that, it's going to flip in direction. And the magnetic field will now be this way. In. It's going to be down instead, out this way, and going up over here instead of down. And again, because the voltage is changing as time goes on, getting bigger, just with reverse polarity, and biggest, and then smaller, because this voltage is changing as time goes on. Even when the polarity stays like this, then the current is going to be changing, so the magnetic field this coil produces is going to be changing, so this magnetic flux is going to be changing, so therefore there will be an induced voltage in the other coil. And when you do the analysis of this, which is what I'm going to be doing in a little bit, what you end up discovering is that whatever the voltage is in the primary coil, like E1, if you divide that by the number of turns in the primary coil, which will be E1 over N1, that's going to be equal to the induced voltage in the secondary coil, E2, divided by the number of turns over there. And this is the equation that you get. Now, this is the equation that you get if you are able to catch all of this magnetic field and make sure that it goes through the other coil. And what we are going to do in the lab is we are going to use like a piece of iron, like this, that's going to go like that. And this piece of iron is just going to help channel the magnetic field from one loop into the other loop. So we're going to put it like this. And then insert it like that. So essentially we're going to have something like this, like iron, like this. And we're gonna put one loop over here and the other loop over there. And this one goes like that, and this one goes like that. So it's just going to be two loops next to one another. So you change the voltage across the ends of this coil here. That changing voltage will give rise to a changing current. The changing current will produce a changing magnetic field. And that magnetic field, since it's changing, it will give rise to a changing magnetic flux through this loop. And since this magnetic flux is changing, there's going to be a voltage over here. And if all of this magnetic flux is channeled into there, so with the iron it helps catch it and send it through the other one, then you end up with this result. And the meaning of this result is actually simple, right? What it means is the following. It means that if, for example, the number of turns over here in one, let's just say this is, just for the sake of argument, this is 100 turns, right? And I set this voltage over here in the primary coil, this is my, now, notice that in this case, the voltage is going to flip back to this, and then it's going to go negative, and then it's going to be plus, and then it's going to be negative, so the polarity is going to be flipping. So the polarity here of the voltage is like, it's like that, and then it's going to be this, and then that, and then this, and then that, and then this, and then this. So as the polarity flips, the direction of the current will be one way, and then the other way, and then one way, and then the other way, throughout the entire coil. So what's going to be happening with this voltage source that is alternating in polarity, like flipping like that, then the current in this coil is going to be alternating in direction. And that is what AC means, an AC source. AC means alternating current. Well, what about the current is alternating? It's the direction in the circuit that's alternating. First to the right, then to the left, then to the right, then to the left in this wire. Here it will be clockwise, counterclockwise, clockwise, counterclockwise, clockwise, counterclockwise, right? These babies right here, 60 hertz. They flip 60 times every second. 60 times 1 second, 60 times the next 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 second, right? So suppose the voltage in the primary coil is, I'm going to choose, how about I'd say 10 volts. Now, given this condition over here, this result, this transformer equation, if you want, for example, over here, this voltage to be, suppose I want this voltage over here to be, I have the source over here, right? But I want to transform this voltage from 10 volts to, let's say, how about I want to transform it to 40 volts. I need more voltage. I want it to be 40 volts. If I want it to be 40 volts over here, then how many turns should I make this coil to have? How many?
400.
Yes, it's because this voltage increased from 10 to 40, it was a factor of 4, then the number of turns has to increase also by a factor of 4. So since this one has 100 turns, this would have to have 400 turns. All I need is another coil with more turns if I want more voltage. And in this case, you started with 10 volts, and I was able to transform that to a higher voltage, right? 40 volts, so this is called a step up transformer. Because I was able to step up the voltage. What if I have 10 volts over here and the number of turns in the primary coil is 100. And suppose I want 5 volts over here. 10 volts happens to be too much. Suppose I want 5 volts. Then how many turns should this secondary coil have? How much? 50, exactly. If this one, if the voltage here is 10 volts and now I only need a half of that, like 5 volts, then I need a half as many turns over here as I have over there. Since here I have 100 turns, I just need 50 turns. And then I'll get 5 volts over there. And in this case, the voltage was reduced from the primary coil being, let's say, 10 volts to 5 volts. That will be called a step down. Transformer. What if the voltage here is 10 volts and I want 1,000 volts? I want 1,000 volts. And if this coil, primary coil, has 100 turns, how many turns should the secondary coil have? 10,000. A factor of 100, yes. It's kind of cute. You figure out how much voltage you need. You just, if you need more voltage, you put more turns in the secondary coils. And if you want twice the voltage in the secondary coil, well, you put twice as many turns in the secondary coil compared to the primary coil. If you want 3 times the voltage, then you put 3 times as many turns in the secondary coil. If you want a third of the voltage in the secondary coil, then you put a third of the number of turns in the secondary coil compared to what you had in the primary coil. That's the result. So what you're going to do in the lab is, I'm going to give you the coils. You'll have like 200 turns. You have another coil with 400 turns, another coil with 800 turns, another coil with 1600 turns. I think there's another coil with 3200 turns. Okay? And so how about we set the primary coil to, I'll use 400 turns. And so we have a coil with 400 turns. So we'll use this as the number 1. And for the secondary coil, we actually have another coil with 200 turns. So it'll be a step down transformer by a factor of, half. And then I'm going to set this to be 400 turns because we have another coil that's similar to that one. And what we're going to see is that, well, whatever voltage we put over here, we should get over there. And then we have another one with 800 turns. So you should get twice as many volts over here as you have over there. And then 1600. So that's a factor of 4. And 3200. And that's a factor of 8. Now, because you'll see this is very rudimentary, very you'll be able to see the guts of it and so on. And this iron stuff that we're going to put over here is not going to manage to capture all the magnetic fields and transfer them from here to there. Instead of getting a factor of 2 over here, you might get a factor of 1.7, 1.8. That's what you'll get, right? So in theory, or if you had a more advanced and fancier transformer, you get closer to a factor of 2. But with the simple apparatus that you play with, maybe you get a factor of 1.8, let's say. And then when you do this one, instead of getting a factor of 4, you might get 3.7 or something like that, right? Not quite. So you'll see, right? But at least, and then what we're gonna do is, we're gonna use like a power supply with a polarity that flips, and we're going to connect a voltmeter over here to measure the voltage in the primary coil. They're called RMS units, root mean square value. So, and then we're going to use the secondary one, and so we're just going to be clicking, changing the voltage in the primary coil, and then like for 3 settings, and then for each setting we'll measure what the voltage is over here. And then you calculate an average by the factor by how much it went up. You'll see I have it in my lab in the hand. It'll be, you pretty much change something, read the 2 values, write it down. Change something, read the 2 voltage values, E1, E2, write it down. Change another setting, read them, and so on. And then you change the number of coils, and you're done this one, then you do that 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 one. It's a pretty straightforward lab. But then you get to see the two coils, and you get to see what happens, and then you get to calculate, the voltage that you measure over here with a voltmeter, and compare it to what you actually measure over there as well, and then you'll just see by how much your result differs from theory, from what you expect, and it's not bad. It's a pretty nice setup. Okay, so as far as the example is concerned, what you do is, it's actually very simple.